Hello students! I am Miss Charisse Rizon and I will be helping you learn about normal distribution. In this video, you will learn how to illustrate a normal random variable and its characteristics, identify regions under the normal curve corresponding to different standard normal values, convert normal random variable to a standard normal variable and vice versa, and compute probabilities and percentiles using the standard normal table. So buckle up and fasten your seatbelts as we go through this lesson. Enjoy the ride! In our past lessons, we learned that there are two types of random variable. First is the discrete random variable, and second is the continuous random variable. Let us recall that a continuous random variable is a random variable that can take any real value within a specified range, like the height of your child or the weight of a newborn baby. The probability distribution for a continuous random variable is called a normal probability distribution or a normal curve. Normal distribution is a very important statistical data distribution pattern occurring in many natural phenomena, such as test scores, blood pressure, lengths of objects produced by machines, and etc. Let's start understanding the concept of the normal curve distribution by sketching the frequency polygon of the following table. This table shows the scores of students in a mathematics quiz. First, let us sketch a frequency polygon of this distribution. In this graph, we can see that students tend to have an average score of 6, and less students got low or high score. Second, let us compute the mean, median, and mode of the distribution. As we can observe, the resulting values of these measures are equal. Since these measures are equal, they all lie at one point, which is the center of the graph. If we will continue to increase the number of students, then in the long run, we can approximate the graph to the shape of a bell. In a specific sense, it is called a normal probability distribution whenever the frequencies are converted to probabilities. A normal distribution has different properties. First, as said earlier, the distribution is bell-shaped. Second, the curve is symmetrical about the mean. This means if we will cut the curve about the mean, we will have balanced proportions of the halves. Third, the mean, median, and mode are of equal values, and when sketched, they coincide at the center of the graph. This means that the mean, median, and mode of the given distribution are located at exactly one point since their values are equal, and they are located at the center of the graph, which indicates the highest peak of the curve. Fourth, the width of the curve is determined by the standard deviation of the distribution. The curve at the right side defines a standard normal curve. A standard normal curve is a normal probability distribution that has mean value equal to 0 and standard deviation equal to 1. Fifth, the curve extends indefinitely approaching the x-axis but never touching it. Thus, the curve is asymptotic to the line. Lastly, the area of the region under the curve is 1. It represents the probability or percentage or proportion associated with a specific sets of measurement values. Any normal distribution, regardless of its mean or standard deviation, conforms to the empirical rule. The empirical rule states that about 68% of the area under the curve falls within one standard deviation of the mean. About 95% of the area under the curve falls within 2 standard deviations of the mean. And nearly the entire distribution, or about 99.7% of the area under the curve, falls within 3 standard deviations of the mean. A normal distribution with a mean of 0 and standard deviation of 1 is called a standard normal distribution. A standard normal distribution is always centered at 0 and has intervals that increase by 1. Each number on the horizontal axis corresponds to a z-score. A z-score tells us how many standard deviations an observation is from the mean. For example, a z-score of -2 tells me that I am 2 standard deviations to the left of the mean, as that z-score of +1.5 tells me that I am 1.5 standard deviations to the right of the mean. Most importantly, The z-score allows us to calculate how much area that specific z-score is associated with, and we can find out the exact area using what we call a z-table, or also called the standard normal table. This table allows us to know the percentage of values between the mean and the z-score. In this table, the top row and the first column correspond to z-values, and all the numbers in the middle correspond to areas. For example, according to the table, a z-score of 1.95 has an area of 0.4744 from the mean. For a z-score of -1, it is the same as looking for the area of +1, which means its area is 0.3413. What if we are asked about the area to the left of a given z-score? Let's consider z equals -2.5. What we can do here first is to try to determine the area between this z-score and the mean. In this case, it is 0.4938. Now, since one of the properties of a normal distribution is that the whole area under its curve is equal to 1, and that the curve is symmetrical about the mean, then it is safe to conclude that the area to the left of the mean is 0.5. Thus, to find the area to the left of z equals -2.5, we just subtract the area to the mean from 0.5. In conclusion, the area to the left of z equals -2.5 is equal to 0.0062. Now, if we are asked to find the area to the left of a z-score greater than the mean, like z equals 2.3, first, we have to determine its area from the mean. According to the table, that is 0.4893. Then, add the area below the mean, which is 0.5. Thus, we have 0.9893 as the area of the whole region below the z-score. But what if we are asked about the area between two z-scores? All we have to do is add both areas from the mean of both z-scores. For example, what is the area between z equals -0.81 and z equals 1.15? Again, we only have to add the areas from the mean of these z-scores. First, we have to determine the area from -0.81 to the mean. According to the table, that is 0.2910. If we get the area from the mean of z equals 1.15, that is 0.3749. Adding both areas, we get 0.6659. Thus, the area between z equals -0.81 and z equals 1.15 is 0.6659. At times, in a given normal distribution, raw scores may be composed of large values, and large values cannot be accommodated at the baseline of the normal curve. Thus, the raw scores have to be transformed into z-scores in order to get meaningful decisions relative to the concepts of finding the equivalent percentage and probability of the given measure of value from the mean. This process is called standardization. Standardization involves using this formula, where z is the z-score, x is the raw score, mu is the population mean, and sigma is the population standard deviation. Suppose in Mrs. Shirley's science class, a student gained a score of 46. What is the z-value of his score if test result is population mean 45 with standard deviation of 2? If we were to draw this normal distribution, we would have 45 located at the center of the distribution because it is the population mean. Each interval will increase by 2 since that is the standard deviation, and the normal value will be located between 45 and 47 since the raw score is 46. To convert this distribution to the standard normal distribution, we will use the formula. The value of x is equal to 46, the value of mu is equal to 45, and the value of sigma is equal to 2, which means that the corresponding z-value of the raw score 46 is 0.25. In the standard normal distribution, z equals 0.5 is located between 0 and 1. Now we are asked about the proportion of students who scored less than 46 on the exam. Since we know that its corresponding z-score is 0.5, we can use the standard distribution table to locate the area of this z-score. According to the table, there is an area of 0.1915 between the mean and z equals 0.5. Now since the z-score is greater than the mean, we add 0.5 to get the area to the left of this z-score. Thus, the proportion of students who scored less than 46 is 0.6915 or 69.15%. Let's consider this another example. The distribution of resting pulse rates of all students at Asian College of Technology was approximately normal with mean 90 beats per minute and standard deviation of 10 beats per minute. The school nurse plans to provide additional screening to students whose resting pulse rates are in the lower 66% of the students who were tested. What is the maximum resting pulse rate at that school for students who will receive additional screening? Round to the nearest whole number. If we try to draw this normal distribution, we would have 90 as its center, the mean. And each interval would increase by 10 because it is the standard deviation. But we are concerned with the lower 66% because that is who is going to be tested. So, if we try to estimate that in the normal distribution, 66% is roughly located here. Meaning, if you are in that score or pulse rate, you have reached the maximum threshold to get additional screening. As you may have noticed in this example, we are not looking for the proportion given a z-value. This time, we are looking for the z-value given a certain probability or percentile. So what we can do is use the standard distribution table and find what z-score is 66% of the distribution. Since 0.66 is an area greater than half of the distribution, we subtract 0.5, giving us a value of 0.16. In this case, we select the lowest z-score that gets us across 0.16. It is at 0.1628 and its corresponding z-score is 0.42. We just have to figure out what value or raw score gives us a z-score of 0.42. We know that z of 0.42 means that is 0.42 standard deviations above the mean. Using the formula, we substitute all our available values, giving us a raw score of x of 94.2. Thus, the maximum resting pulse rate required for students to receive additional screening is 94.2. Rounding it off to the nearest whole number, that is 94 beats per minute. So that's all for our lesson on normal distribution. I hope you all have learned and enjoyed our discussion. See you next time. Bye!